Good morning to all who are present here. On behalf of Sri Krishna College of Engineering and Technology, Coimbatore, I am happy to welcome our chief guest, Dr.Lovelyn Rose. Currently, she is working as Associate Professor in Department of Computer Science and Engineering in PSG College of Technology, Coimbatore. She has 18 years of academic experience. She has been sanctioned a research project from DST ICPS to the tune of rupees 75 lakhs on design and implementation of e-learning system using deep learning based on audio and video speech recognition for hearing impact in native language. She is currently consulting on AI and ML for business IT sectors like Robert Bosch and Advantech Data Link Solutions. She has given series of lectures to the managers of Robert Bosch on AI and ML. She has published more than 50 research papers. She has been a resource person for several national level workshop, conference and symposium. Today, she is with us to share her knowledge on back propagation. Thank you, ma'am, for joining us. The session is yours, ma'am.
Thank you. Thank you. Thanks, ma'am. So let me start off by checking out what audience I have first so that I know where to start, where to end. Okay. I have 1.5 hours with me. Back propagation is the topic which is assigned, and it is not an easy topic. Okay. Because I remember the first time I tried to understand it, it took me days. Okay. To just get the gist of, okay, what are they trying to tell? So let me first get a feel of what you know about ANN and what you don't know about ANN, because that will help me to start at a level and then build it up so that you can also understand the back propagation clearly. Okay, so that being the intention, can you tell me, one of you can probably tell me, do you know what is an artificial neural network? Do you know what is a training set? Do you know what are the input nodes you're supposed to give? What is the output node you're supposed to give? What is a hidden layer? Do you have a fair idea of this? If someone can help me with this information, it's much easier for me to proceed from there. Okay, so Rupa ma'am has said yes. Okay, so it is under the assumption that you are clear of the basics in deep learning. Okay, so with that premise, let me start it off. So there are 3 parts for my lecture. The first part is I think I'll just switch off my video. Please start from the basics of hidden layer. Okay. And okay. Fine. Somewhat, please start from the basics and other notes. Fine. If that is the case, as I proceed with the forward pass, I will also deal with the basics. Okay. So that's how I will be proceeding. I'll switch on the video. Switch it off. Okay. So I'll start with the forward pass. So as I said, this is going to be of a higher level if I start from here. So we make certain assumptions on what problem we are trying to solve. The first assumption I'm going to make is I'm going to solve a regression problem using artificial neural network. Okay. Now, the reason I am saying I'm taking a regression problem is the way I would do a back propagation and I would do the entire thing would be different. Back propagation would be the same, but the way I look at my output node will be very different when I do a regression and when I do a classification. Okay. So what is regression and what is classification? Very, very simple. Fine. So when you say regression, I think I should have, okay, fine. So when I use the word regression, the main thing about it is the final output that you're trying to get is going to be real values. What do you mean by real values? Very commonly speaking, we say it's about stock market. Okay. So Okay, I think I have an issue here when it comes to presentation. I have set a timer and that's really difficult. I'll just check out if I can do something about it. Okay, so I want to remove all animations because this will help me. Okay, fine. So now we're not going to have a problem. So the input can be a set of features. The output is going to be a number. Okay. So when you say regression, we are trying to get a number as output. Okay. So generally speaking, if I'm trying to get one number as output, I will have one output node. If I'm going to have, I'm sure all of you have heard of the word bounding box regression. Okay. Does anyone not know what is a bounding box? Okay. So when you say a bounding box, if you can see, you are actually trying to draw a box around something. Okay. For example, if I draw a box around this, okay, I'm drawing a box around it. I know it's not looking like a box, but assume it's a rectangle. Okay. So this is the rectangle I'm trying to draw. Why am I trying to draw this rectangle? I'm trying to find that position in my screen which has a object in it. Okay, so that is what you call as object detection, right? So what is this object detection? I am trying to find one rectangular object in my screen. And I am telling while giving the training data set, this rectangular object is found in this position. Okay. So how will I mention the position? I will give the top left coordinates and I will give the bottom right coordinates. Very, very simple, right? So I will say this is at a position, let's say 25 and 100, and this is at a position, let's say, if this is 25, this has to be greater than that. So probably 50 and 200. So I'm telling this location is 25 and 100 and this location is 50 and 200. Please note what I am trying to train my network and get the answer here is actually 4 numbers. Please let me know if you do not understand what I'm speaking. Because unless you know what is regression, we cannot move to backpropagation per se. So when you say regression, your output, you're trying to get a number. Very, very simply, all the time, what you would have seen is a stock market prediction. What happens in a stock market prediction? I will give yesterday's value. I will give a bunch of all the sentiments. I will give their account balance. Okay, I'll give the statement of the company for the year. And I will try to predict what is the stock value tomorrow. So I am expecting only one output there. This is a regression problem. Very simple. But I'm also trying to introduce you to another type of regression problem, which is very prevalent nowadays, which is I'm trying to draw a rectangle. And when I'm trying to draw a rectangle, all I'm trying to figure out is, okay, what is the top left value? What is the bottom left value? How many values am I expecting here? How many values am I expecting here? How many values am I trying to get as an output here? I'm actually waiting for an answer. Any answer would do. Yes. 1. Okay. Any other answer? Fine. 4. Okay. Ms. Ruma, can you tell me why you said the answer as 4? Padmashini says 4. Can anyone tell me, switch on your mic and tell me why do you say it's 4? Anyone? There are 4 different numbers I'm trying to figure out. Correct? Top left, I have an X value and a Y value. Bottom right, I have an X value and a Y value. So there are basically 4 different values that I'm trying to figure out here. Right? Okay. So in this regression problem, I have 4 numbers to be output. So what will be the number of output nodes? Obviously, it will be 4. Okay. So the first thing is clear. Depending on how many numbers I want as output, I set the number of output nodes. Okay. All that is well and good now. I have my output nodes. I'm just checking out if I have some okay. I'll just use this. So I have an output node, and the number of output nodes, I'm determining it with the help of the idea as to how many output I want. Okay, fine. Now, what about your input nodes? All of us know as many features, so many input nodes. Okay, so another question to you. Again, first, I would like to know how much you all know, and also like how much I need to ignore. The question here is, I said as many input nodes, okay, input features. If I have 5 features, I will have 5 nodes in the input layer. If I have 2 features, I will have 2 nodes in the input layer. And I did a code using this, using PyTorch. Okay, I very beautifully, I had to do a regression. I gave the input, I gave the output node. It was actually a data set which had some almost 1 lakh data with it. So my data set is also pretty huge. Okay, I have a very nice data set with me. And I started training this data set. Even after 15 epochs, what happened for me is the loss did not reduce below 40. My loss started at 120 and it refused to go even below 40. I tried all the 40 epochs, 15 epochs, and I could not get it reduced to less than 40. Okay. Can anyone tell me what I did wrong? I gave the features, I got the output. When I gave the features, I forgot to do something initially, which is very, very important when you want to train a a machine learning model. What should be the nature of your input? How should your features be? Can anyone tell me this? When you want your loss to reduce, it won't reduce beyond a level because of a major mistake you did when you gave the input. Can you tell me what? Any answers? Define the accuracy level. Not exactly. A very important step in the input, which when you do machine learning or deep learning, you have to hold on to. Normalization. Okay. I know that normalization looks like such a simple word, as if like, okay, you normalize your data and then you give it as input. Okay. Normalization is so important that if you do not normalize your data properly, I'm telling you, your output will not be right. Okay. Of course, having your input and adhering to the normal distribution, of course, helps it much more. But even if you don't have your input adhering to a normal distribution, even if you normalize your data to fall within the range of 0 and 1, sometimes it works wonders. Okay. So now, the first word, regression. Okay. So what are we going to do? We are going to give a set of features. If there are 10 features, there will be 10 input nodes. And I have also mentioned to you, ensure you normalize your data and give it as input. Not only for an ANN, it applies to most of your, your machine learning models. Okay. That's the first thing. So for my lecture on backpropagation, I am assuming the problem statement to be regression. Okay. And features, of course, it doesn't matter for us right now. Fine. Now comes the activation function. Then we shall go to the loss function. So when you go to the activation function, I think I should take a slightly bigger, I was not expecting to take from the basics. So I have a different video with me, a presentation with me. Since I have to start from the basics, let me look for a network which is slightly bigger. Yeah, this is exactly, let me look at it. Okay, so I have more than one input, more than one output. Okay, fine. Now, first thing before we start, what is meant by the word model? So right now we know how the input should be, we know how the output should be. Okay, but now the next thing is, I say I'm creating a model, right? Whether it's a H5 or a pickle, you say you're creating a model. What is this word model? What do you mean by the word model? What are you doing? Anyone? Anyone? Predicting. Okay. The model is going to predict. Am I right? But what is the model? It is a program. Okay, Carolyn. Any other answer? It's an algorithm. It's an estimation. Okay, any other answer? Okay. There might be an equation. There might be a simple formula. Supriya has raised a hand. Would you like to answer? Or do you have a question? It's a hypothesis. Very good. I do not know if you say the word framework, but I would accept the word more concrete. A hypothesis is more assumptual. It's more concrete. Okay. I think someone raised their hand. Do you want to ask a question or answer? Fine. When I say state of system, that which relates to act of actual output. Okay. Very beautiful answers. Now I will tell it in the way I look at it. Okay. When I say the word model, for me, it is either a formula, okay, it's an equation, or it's an if-then rules. As one person pointed out, it's an algorithm, whatever it might be. Right? Now that we know what is a model, so what is a model? Here in ANN, what is a model? Okay, I am a little handicapped today because as you know, online classes, it's from the houses and it's always easier for us when we write something. So I'm having a little difficulty in writing. So let me check out that also. Okay, fine. Okay, let me write in this. When I say a model, fine, I am trying to come up with an equation. Very simply speaking, let's say the equation is, okay, let's say the equation is let's take a very simple equation. Y is equal to mx plus c. All of us know this equation, so no difficulty there. Okay, so I'm trying to find a straight line. Am I right? What I'm trying to do is I'm trying to find a straight line. That's the model I'm trying to find. Are we clear with what the model is? I am trying to find the straight line, which means I'm trying to find y is equal to mx plus c, which means x is my data set, okay, which is my training data. And that training data is going to fit into a line because it is regression. If it was classification, that training data would split my data into two classes. Please let me know if I'm going above your head. Okay, please let me know that also. Since it's regression, the training data X is trying to fit all my data along a straight line. We understand what this y is equal to mx plus c is? Now, when I draw the straight line, okay, when I draw the straight line, I can draw the straight line like this. Yes? Okay. Now, when I draw the straight line can look like this. The straight line can look like this, right? The straight line can look like this. I do not know where. Okay, I do not know what the straight line is. But all the difference between my straight lines is dependent on the slope. Slope is the angle in which it is moving, and the displacement. Am I right? Right? Your y-intercept and your angle. Your y-intercept given by c, your angle given by slope. Now, when I say I'm trying to find a straight line, when I try to do a regression problem, what is this straight line? I have lot of data points in my, data set. All these data points are going to kind of lie along this line. So I'm going to find that line along which all my data points lie. That is what is this. Now, okay, and I also say that where this line is drawn and how this line is drawn depends upon my M and depends upon my C. Okay. Now, what is my model? The model that I'm actually drawing here is, when I draw this line, okay, I have probably the M value to be, let's say 5. Okay. And here again, it's still 5, but the y-intercept has changed, right? So probably the first time the y-intercept was at 5, and I have another equation. Oh my God. Okay, and I have another equation, which is probably say 5x plus 10. What your machine learning model tries to do when it does an artificial neural network is, please note I've taken a very simple formula, simple straight line. It tries to find whether it has to be 5 and 10 or whether it has to be 5 and 5. Right? This, can you tell me what is the word we use instead of this? We use the word weights. Okay? So when it learns the weights, it learns what is the angle in which my formula should go, my line should go. When it learns the y-intercept, in other words, you call it as your bias, it learns what should be the displacement of your model along the y-axis. Okay? Any doubts here, questions here? Have I gone above anyone's head? Shall I continue? Okay. So what we have simply known here is, when I say a model, I have to find some weights, I have to find some bias, and it fits itself in a equation. I get some structure, and that structure which I get is the model. So we took a very, very simple example, but the point here is the structure can be as difficult as, let me draw it. Where do I get the draw? Okay, it's here. It can be as okay, it can be like this and 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 this. Even this can be a model. So what is the work of your artificial neural network? The work of your artificial neural network is to find out whether the output should be this or the output should be this. So you might ask me, see, this is very, very simple for me to figure out. It is just a straight line. It is y is equal to mx plus c. I can think about it in my mind. But how do I get a structure like this as my model? That is when your hidden units come into play. When you have the concept of hidden units, what happens is it tries to find multiple equations and it combines them. So if you look at this particular thing, I have one equation from here to here, I have another equation from here to here, I have another equation from here to here, and I have another equation from here to here. Your hidden layer has the ability to combine all these equations and show you as one single model, and that is the power of your hidden layer. Okay? That's why you call something called as a universal approximation theorem. The universal approximation theorem is very, very simple. when you use an activation function, which is a nonlinear function, your hidden layers, if you have sufficient number of hidden layers, okay, it has the ability to learn any equation you want, whether it is a sine equation, a tan equation, whichever equation you want, cos theta plus say secant theta, whichever equation you want, it has the ability to learn it and then put the weights accordingly. Okay, so what your artificial neural network does is, when I say it learns a model, it learns the weights, it learns the bias, and figures out the equation which it has to fit into so that it represents the data set. Am I okay? So this is all about the basics. I think it's time for me to move on to the actual crux of our thing, which is backpropagation. Before I move on, any other questions? Anything on the basics? Okay, so let me move on. So now what is happening? You have something called as activation function. So this activation function is going to determine how should be the output of every node. And I just mentioned that the universal approximation theorem says, okay, if you have a nonlinear activation function, then you can learn any equation. Do you understand this? Okay. Can you name me some nonlinear activation functions and some linear activation functions? Okay, tell me a simple linear activation function. Let's start with that. What's a linear activation function? Most simple linear activation function? Yes?
Step function.
Step function? Yes. Then? Linear? Is step function linear? Okay, step function has a problem with differentiation. That is why it doesn't work well. But I don't think you call it as linear.
Ramp.
Yes.
ReLU, ramp.
ReLU and?
ReLU. Sigmoidal.
Is linear or non-linear? Let's get that clear. This ReLU and sigmoid and tan H and leaky ReLU, are they linear or non-linear? What do you mean by the word linear? Padmashri says it's non-linear. Can you tell me one linear? Because only when you know what is linear, you will know this activation function I should not use here. Because if you use a linear activation function in your hidden layers, okay, you might not get a good result. You will not get a good result. It's not might not. When you have a big data set, you will not get a good result. So you should avoid that. What is that? Any other? Okay, let me draw and show you. Okay, slope unity. Can I know what it means by slope unity? Let me draw a simple thing and ask you. Okay. This is a linear function, which means as one increases, the other increases in the same proportion. F of x is equal to x. Am I right? F of x is equal to x. That's your identity function. And that is a linear function. This linear function you should avoid in your hidden layers. Okay. Whatever you give as an input, the same thing comes out as output. That is what you call as your linear activation. And this should be avoided in the hidden layers. But linear activation is used in one particular place very commonly. Anyone who knows that? Yes? Where do you see? I just said, and passing through the origin. Okay, Bhagya, thank you. Now, if you say activation function, a linear activation, I just told you, don't use it, it's not good. Okay? But it is supposed to be used in one layer. Can anyone tell me in which layer? whatever you give as input, you want it as the output, and it will not affect your training process either. Any idea? Okay. Especially in regression problem, linear activation is commonly used in the last layer. Okay. In the output layer, you use a linear activation. You do not use a linear activation in any other layers. Fine. The other common things that you said, like your ReLU or your sigmoid or your tan H, okay, there are many small variations in that also. All those are extremely good, okay, in the hidden layers. They help to give a non-linear activation. Is there any doubt? Okay. So now we know what I mean by this activation function. Okay, I'm still in the first slide. Okay, fine. So when you, I think someone has their mic on, that's kind of echoing for me. Can you just check your mic? Someone has unmuted the mic by mistake. It's echoing a little. So when you say this activation function, what does this sigmoid do? It's more like a normalization in that layer. Okay. I think someone has to unmute their mic.
Yes, ma'am. Venkatramanan sir. Venkatramanan sir, kindly mute sir.
Okay. Fine. Can you still hear me over it? If you all can still hear me, I'll
There's lot of disturbance.
Okay. So I'll still continue then, if you can hear me.
As the organizer, maybe they can mute Venkatramana sir.
Yes, ma'am. I have muted, ma'am.
Okay. Thank you.
Yeah, thank you so much.
Okay. So now, so we were looking at this activation function, and we said when to use linear activation, when to use non-linear activation. There's one other major aspect of the sigmoid activation. These are all called as squashing functions, right? So when you say a squashing function, it literally kind of compresses, squashes it and puts it inside a range. Okay. It is also having the effect of a normalization. When you use a sigmoid or a tan H, whatever input you give, okay, when it's a sigmoid, your output will always be a value between 0 and 1. Okay. And similarly, when you use a tan H, your output will always be a value between -1 and 1. Right? Okay. So now, in this particular problem, we are going to use a sigmoid activation to teach back propagation. Right? And then we are going to use the concept of a stochastic gradient descent. Do we know what is a stochastic gradient descent? Do you want me to tell you what is a stochastic gradient descent, or shall we move from there by telling this is the stochastic gradient descent? There's a difference between saying a gradient descent, a stochastic gradient descent, and a mini batch gradient descent. Some feedback would help. Shall we see what is a gradient descent? Yes, no. Okay. Something on the chat window can help. Yes or a no for gradient descent, stochastic gradient descent. Okay, fine. So now, when you use a gradient descent algorithm, I will just tell you what it does. So we need to first know what we mean by this word training. Okay, so when you know what the word training means, we will also know how to do what is the stochastic gradient descent doing here and what this loss function is doing here. Okay, so now this is what we are going to use for the rest of it. Okay, and a little note on the loss functions. When you say a loss function, the loss function, there are many loss functions, and it is extremely important that you know what loss function to use for which problem. It is not like you try out all the loss functions and you say, okay, this works well, that doesn't work well, I will do this, I will not do that. No, it doesn't work like that. When you have a regression problem, acceptably good loss function is the mean square error. Okay, mean square error has its own set of advantages. Like, okay, it has the ability to give you the first gradient when you differentiate. Okay, look at this, you need a differentiation here, right? Fine. So when you differentiate, the answer that you get is very simple to calculate when you have a squared error loss. Fine. It is the error that you're differentiating. Please have a look at this. First thing. So what loss function you use depends upon the task at hand. When you're using a regression, you will probably be using something like a mean square error or a mean absolute error. Okay. And you have a lot of variations in that, like there's a logarithm there, there's a logarithm here, etc., etc. It depends what best suits your application. When you use a classification problem, your final layer, usually nowadays we make use of a softmax classifier. It is acceptable to use a sigmoid classifier. Okay. And it is also totally acceptable that you use a cross entropy loss with your softmax layer rather than a mean square error. Let me see if I'm making sense to you. Okay. If I'm having a cross entropy, if I'm having a classification problem, the last layer, the activation function will be a softmax activation. When you use a softmax activation, along with it, you have certain loss functions which are acceptable, like the cross entropy loss when you have multiple classification problem, or the binary cross entropy when your classification is a binary classification problem. So you have to choose which loss function you have to take, which activation function you take. You have to make that choice correctly. It is not a trial and error, it is knowledge. Okay, you have to learn about these. The next thing that is very, very crucial when you train is the gradient descent algorithm you use or the optimization technique you use. What do you mean by this word optimization technique or the gradient descent algorithm you use? Okay. Nowadays, most of the time when you want to, okay, so how does the training work? So let's see that 1 minute and then come to this. How does the training work? You give an input, goes to the hidden layer, goes to the output layer, predicts an output. Okay. So the first time they came up with the concept of two-layered perceptron, that was the first time they used the concept of training, but of course the algorithm used in updating the weights was different in a two-layered perceptron initially. Okay. So what happens in this is you have a two-layered perceptron and transition, let me just cut it. None. Okay. Now I think I'll not have a problem. What is happening? I'm giving the first row in my training set as input, right? That's how we look at it. It does some activation, goes to the hidden layer, okay, goes to the output layer. In the hidden layer, you might have some activation function. So whatever you give as input changes its value, goes to the output layer, and you have a value. Okay. Now, what I have done in this simple example is my input, I've taken only one value. So my input is a 0.2 and the output I'm expecting is a 0.3. But obviously, initially, okay, again, weight initialization. Next question. How should you initialize the weights? Any answers? What is the best way to initialize weights? Answers? It would really help if I get some answer. Ma'am, is it possible for the participants to still chat with me? In-call messages can be sent, right? Okay. What's the best way to initialize the weights? Fine. Now, some amount of feedback. The reason I ask here is, okay, people are listening, so I really have to talk properly. Okay, so that's the intention there. So, anyone? How do you initialize the weights? Any answer? Any answer? Any answer? Okay. So when you want to initialize the weights, the best way to initialize weights is randomly.
Ma'am, we have given that in the chat window.
They've given it, then how come I'm looking somewhere else, nothing else. Thank you.
Thank you.
I was in some place and I was like, oh my God, people have left. People are not listening. Okay. Thank you, ma'am. Thank you. Okay. So, I also see a yes there. Is that for gradient descent, Padmashini,
Yes,
ma'am?
ma'am. That was for the gradient stochastic.
I actually have a totally different slide for all this kind of information. Okay. I'm still with the basics. Fine. If I have to teach gradient descent, I have to use a different slide. Let me check out right now with this setup because I have only another 45 minutes more. I'll try how to do this. Fine. So, very good. You assign random values. Now tell me, what should you not assign? What kind of value should you not assign when you try to initialize? See, when you know something you're supposed to do, you should also know what you're never supposed to do. Gradient descent will never work if you assign all your weights to, any answer? 0. Okay. Never initialize weights to 0. Never have an uniform initialization. Okay. And there are some other new initialization techniques like the Z initialization, XC. Okay. It's XC initialization. Okay. And the Xavier initialization, all inbuilt in Keras and PyTorch, which give good results when you do CNN, or it depends upon your architecture. Okay, so this is about weight initialization. Fine. So now we also know how to initialize our weights. I have initialized my weights and I am giving. I am getting obviously I will get a wrong answer. Okay, there's nothing to say that, okay, if I pass in 2, I will get 0.2 there. I am passing it through something. It is doing some operation. It is giving some output. How can the input and the output be the same? No way it's going to be the same. It has to be different. Okay. The whole point about training is finding the final values of your weights and your bias such that your data set is adhering to the output. So what happens first? I have a 0.2, gives it as input. Okay, I'm getting a 0.3. No, this is not what I'm supposed to get. So you're giving this feedback back to your model or your architecture, your network. Okay, you're telling your network again, no, what I expected is 0.2. You have given me 0.3. The weights and the bias which you have given there are wrong. Change it. Now I should know how to change it. This is where the whole difference lies. Okay, how should I change my weights? So if I have to know how I should change my weight and how much I should change my weight, I need to have a mechanism, and that mechanism is called as your gradient descent mechanism. Okay, so when you say the gradient descent, as I said, I have it all these in different slide. It was not supposed to be taught today. So let me just, as I speak, also try to connect my hard disk. Okay, so what happens in your gradient descent? The major idea is the input is different from my output. I want my input to be getting closer to the output. At this juncture, let me ask you another question. All this is right. Okay. I have a data set with me in which, please note my words. I have a data set with me, and my data set is such that the inputs that I have are random inputs. There is no pattern in the input. Absolutely no pattern in the input. Okay. I'm just trying to get the right the deep learning, ANN and deep learning. I think I should have in this. Let me check it out. This is my simplified version of the ANN architecture. But what we are supposed to be dealing today is the hi-fi version of ANN architecture. Okay. So this I'm sure all of you must have seen on and off again. Okay. Now there is something. Okay. What it is please let's understand this clearly. I have a network with me. The input which I got is different from the output which I have got. And then I asked you a question. I'm having a data set with me. Okay. My data set is such that there is no pattern in the data. Okay. Can you still try to train the data set and get a model? This is the question. I have a data set. There is no pattern in the data. It's a random data set. Okay. Can I still try and learn the model? A yes or a no? Is it yes or a no? You can still learn? Yes. Okay. But remember, feed in garbage, you get garbage. Okay. The reality about a machine learning model is it tries to learn patterns. If you are going to feed in junk and say, okay, learn a pattern, it will learn something. Please note, it will learn something. I think that's how probably the first time they learned about this cats in the, what is that? YouTube architecture, the CNN architecture, the initial days, that's how I think they initially learned it. Okay. I'm getting quite a lot of chat. Very, thanks a lot. I think it makes a lot of sense. The first thing you realize when you create your machine learning model is if your data set is wrong, your output is wrong. Please note, you will get an output. It doesn't mean you're not going to get an output. It will try to do something. It will try to learn something. But it will try to learn something which is wrong. See, it's simple as that. There is no pattern. But it is still trying to learn something. It will learn. But it's not the right pattern. You will think you've got a pattern out of it. But the fact is everything is wrong about it. So when you feed in your data set, I will tell you a very small example why I am telling you this. Let's take a very simple problem, which is sentiment analysis. Okay, I think all of us know it. I can do sentiment analysis on movies. I can do sentiment analysis on mobile. Am I right? Okay. Now what you are doing is you're taking a beautiful data set. You are combining every random thing that you find. Certain models work well. I'm not going into that field at all, of course. Okay. Randomly, you're collecting something. It is not even common, something. You're just collecting some random data and you're telling it, find a model. You will get a model. It will start predicting wrong. You give a data set in such a way that it is able to find the pattern in it when there is really a pattern. Rupa ma'am says you have to clean the data. Very, very important. You have to clean the data. But I will also ask you, you also have the tendency to introduce noise, especially when you have a deep learning model, which means you will introduce noise into the data. You don't need a cleaned data. Okay. Why do we do that? You don't actually need a perfectly cleaned data. Why? If you give a perfectly cleaned data, what major, disadvantage can happen? Can you give me that word? Overfitting. Okay, the word there is overfitting. You don't want to give a perfect data. Why do we not want to give a perfect data? A perfect data, okay, I was talking about the sentiment analysis. I'm giving a very perfect data to learn all the movie reviews. Okay, perfectly learn the movie reviews. I'm trying to give it slightly different. Okay, it perfectly learns the movie reviews, which means its ability to learn on the training data set is perfect, 100%. I'm giving a review which is slightly different from the mobile domain. Okay. Am I expected to learn it? Yes, it is also a sentiment analysis problem. The domain slightly varies. In that case, when your excuse me, when your model perfectly learns on your perfect data, it cannot learn when on a slightly different data. On an overtly different data, it need not learn. Okay, that is acceptable. You're giving a like one person. We're doing a project for a person. He said, I have a lot of receipts with me. I will give you the receipts. I want you to do an OCR and give me in that. Made sense to me. I told him, okay, we will do an OCR. Okay, invoice data recognition. Then he said, see, I will use that invoice data recognition model that you give me, but I also have bank statements with that. This bank statements also, for that I will use this model. I said, it doesn't make sense. You're talking about a totally different problem statement. You get the difference here? Okay. Invoice data extraction and the bank statement data extraction, if the model is very different, if the input is different and the output is very different, you don't club them. That was what I was talking about when I said, don't try to find a pattern when there is no pattern. But what this person is telling is, okay, okay, you take an invoice data, okay, you perfectly learn the OCR in it, but okay. But the second thing I'm going to talk about is he's giving me an invoice data set. I will train in it. Okay, it is for his company. But if he's going to give me a totally different invoice, please note again, I'm using the word invoice, which I'm not trained on. I should still be able to figure that out. That is what you call as generalization. This generalization can never happen when you overfit. What do you mean by this word overfit? My training set perfectly learn my model. If your training set is like this, what is that? One line here and one line there, it will just learn perfectly my training data set. I'll just take some example. For example, these are my, what's it? Oh my God. I just want to draw dots, that's all. Okay, assume there are some, let's just see if I have some, oh my God. I just want that, okay, I think this is helpful. Okay, there are a lot of data points here. Okay, these are all my, this is one training row. This is another training row, another row, another row. Okay. One model, what it is learning is, it is learning like this perfectly. This is the curve it is learning. You get me? Another model, what is it learning? It is learning this line. The model which is learning this exactly, passing through every single thing, is giving me 100% accuracy on the training data set. Okay, but there is something called as a generalization error. What do you mean by generalization error? On unseen data, when I give it, this model is abysmal. The performance is really poor. Why is the performance so poor? Because it learned the training data set perfectly. You want to avoid it. You want to avoid overfitting. So it is sometimes okay to have some noise in it. Okay, very good. Similarly, it is okay to have outliers. It is okay to have outliers, though you don't, but if you overfit, Especially when there is an outlier, your model is going to be really bad. It is always best to remove outliers before giving it into the model. How do you remove an outlier? Very, very simply speaking, any idea? The simplest is using your standard deviation. Take your data set, everything above a 1.5 standard deviation, remove it. It's a very simple way to figure out an outlier. You don't have to have any fancy algorithm for that. Remove those rows and then feed it into the model. Your model is decent enough. But never learn too much. Okay, your generalization will become poor. This is a problem not in machine learning, but rather a problem in deep learning, because the amount of data you have is very huge and the amount of resources at your disposal is so huge. So what will you think? See, I have so much of data with me. I have all the resources with me. I'll keep on training. You will keep on training. You will perfectly learn everything. You will learn it too perfectly. Okay. That is why you have a lot of options now. Like, can you tell me some of the options we use? One major option we are using now is a concept called as dropout. Dropout helps you to reduce your, your overfitting. It is usually used in the hidden layers and in the input layer. Very, very important concept. Okay, so that you don't overfit your data. You don't want your architecture to perfectly learn. Very, very simple. Any questions so far? Okay. If not, we were looking at, so I was looking at the second part of it. Oh my God, I don't know how. We were looking at the second part of it, which is, okay, fine. Oh. I am really unable to get to that slide. Okay. So we were looking at what is it? What is gradient descent? Okay. So we were just stuck in the first slide where I said you have to give an input, get an output. The expected and the result are different. So what should I do? I should change the weights. Now the second question is, how do you change the weights? So how do you change the weights is a very, very difficult thing to answer. So initially when they did the perceptron, they had one method to do it, but it worked only with binary classification. Okay, they could not do it for everything, but then of course perceptron was the first time they introduced the concept of weights and bias, which helped in getting the concept of training. Very good about perceptron there, but the algorithm they used could not be used for multi-layered perceptron kind of a concept. So what you did is, they came up with the next thing, which is gradient descent, which was something which was there way back in, way back in 1840s. Okay. So the idea behind this gradient descent is, just look at the number of optimization algorithms you have. Why am I having all these algorithms? I have an input, I have an output. Randomly I gave it, it is giving me an output. But now I wanted to change the weights in such a way that it is similar to my output. Okay, so that whenever I give this input, this is the output I will get. Like that, change the weights. This is the way. This is the work of optimization algorithms. And of course, the most common among them is your back propagation. Okay. What you do is, you take the weight, starting here. Randomly, I initialized, I gave the weight as 0.1. Okay. Please note, an acceptable weight is between usually -25 to 25. If it goes even beyond that, you're having a very bad model. There's something really wrong with your architecture. Okay. So initially, I start with a 0.1, but it is random. Now, certain times, please note this, certain times, when you have a proper activation function, which is monotonic in nature. What is the meaning of the word monotonic? Any idea of the word monotonic? Okay, monotonic means as one increases, the other also increases. As one decreases, the other also decreases. That's monotonic. Certain activation functions, okay, have the tendency to be monotonic. Right? Now, what are the monotonic functions? You can either have a sigmoid, a tan H, a ReLU. All these have a very good idea around monotonic functions in such a way that when you draw the error that you get, okay, I don't want to go above your head. Let me tell you, for different weights, if you plot the different errors that you get, okay, you have different weights, you plot the different errors that you can get, the function that you get will be a convex function like this. Got it? So the activation function is very, very important, not only to normalize your data, not only to give the right, not only for universal approximation, it is also helping in giving an error surface. They call this as an error surface. What is an error surface? For different weights, what is the error you're getting? This error surface that you get, okay, should be convex. If it is convex, wherever you start, I can use a technique called as gradient descent, wherein it should go from here to the lowest point. Okay, how does it go from here to the lowest point? Very simple. I draw a tangent at this place, and this tangent, I will take the slope. When I take the slope of this tangent, this slope will give me the direction in which it will have to move. Okay, please note, this is a convex function. It looks like a parabola. Okay, assume this is y is equal to x square. Assume this is y is equal to x square. So I want to find the minimum point in this function. When I find the minimum point in this function, my error is the minimum. Very, very simple. My error is looking like a convex function. My weight is somewhere along this function. I want my weight to touch this part. Okay. Only then my error is the minimum, which means my data set has been learned. How do I do it? I take the tangent of that function. The tangent will give me the direction in which this point will have to move to go to the maximum of this function. Okay, if I get the slope, it will tell me you go along this direction. It will give you the maximum, you can reach the maximum of this function. But what I want to know is, no, I don't want to go to the maximum, I want to go to the minimum of the function. So all you do is, what you say, this is your initial weight, okay? If you go along this direction, how do you say that direction? You say the direction in terms of the slope. What is a slope? Simply speaking, a slope says, how much does your point move along the y-axis when you move along the x-axis? That's your slope. I move 10 units along x-axis. In that case, how much will it move along y-axis? That is your slope. So simply speaking, what is it? Nothing else but your derivation. How much should your j of w move, okay, when your w moves? Which means d of j of w by dw. That is your slope. This slope gives me the direction. So what should I do if I want to go to the top of the to the highest value in the function? I am starting here. My weight is x. I am telling x plus differentiation of j of w by dw will take me to the maximum point of function. But now I want to go to the minimum. So what do? Nothing. Wherever I am, I go in the reverse direction. I go to minus dc by dw. Okay. This is simply gradient descent. But when we want to use stochastic gradient descent, let's see the difference. When you see a gradient descent algorithm, the gradient descent algorithm works in such a way that first I will give my entire set of data set. Okay, I will give my entire data set. First row I will give, it will say error is 1. Let's assume. Second row I will say give, it will say the error is 0. Third row I will give, it is saying the error is 2. It is 1, 0 and 2. Those are the 3 errors I have got. I will add all the 3 errors and then I will change the weights. This is what happens when you have a gradient descent algorithm. Okay, but when you have a stochastic gradient descent algorithm, okay, when you have a stochastic gradient descent algorithm, it will not change after it does 1 plus 0 plus 3. First, it will see the first row. It will see it is 1. It will change the weight. Then it will give the second row. Then it will change the weight. The stochastic gradient descent is much better than gradient descent. Am I going a little above your head? Anything you don't understand here? Is there anything you don't understand? I don't want to use too many technical. I know I'm using too many technical terms. Anyone? Okay. Fine. So now, when I'm using a stochastic gradient descent, what I do is, I simply say, okay, I take the first row, I change it, I take the second row, I change it, I take the third row, I change it. This is supposed to be good to avoid your, okay, see that one major problem is with gradient descent is very, very simple. Most of us know it will get stuck in the local minima. Okay, so what is it when I say it gets stuck in the local minima? Something like, let's see if I have that figure with me. No. Okay, something like this. I just wanted a pen. Okay. When I say local minima, it's good if your function is like this and this and this. This is good. But what if it is like this and this and this and this? It's possible, right? Your error function is like this. In this case, if you start your weight here, it will get stuck here. But actually, you want to reach here. This is what you call as getting stuck in the local minima. Gradient descent has a problem wherein it can get stuck in the local minima. See, it will look like a very simple thing for you. But certain times when you do actual programs, your loss function will not reduce at all. Okay? In that case, try changing your loss function. Okay? Because it is so getting stuck here, it is unable to, sorry, you have to change your optimization technique. Okay, it is so getting stuck here, it is just unable to reach the actual minimum. For this, one major thing we do is use something called as a stochastic gradient descent. Stochastic gradient descent, what it will do, row by row, it will change the weights. This has a tendency to not get stuck in the local minima. Why? You can go and have a look at it. Okay, there's a proof for that. But there's a problem with stochastic gradient descent. How many times are you changing the weights? That's a huge computational cost. So gradient descent, it adds everything, changes the weight once, having a tendency to get stuck in the local minima. Stochastic gradient descent, very good, doesn't get stuck in the local minima, but the computational cost is increasing. Okay. So what you do is, you don't do gradient descent, you don't do stochastic gradient descent, but rather we always do something called as batched gradient descent, wherein you take batch sizes. Normal batch sizes used are 32, 64, okay, 256. 32 and 64 are very acceptable in a deep learning scenario. And For every 32 training data, it changes. So it doesn't change for one, it doesn't change for everything, but in batches it will do it. Okay. So after one batch, it will change the weights. Then it will do the next batch, it will change the weights. Okay. So there is a summation for every batch. Any questions here? Okay. So this is what happens during a stochastic gradient descent. Fine. So now the first slide should be clear. We know what we are solving. We know what is a loss function. We know what is an activation function. And we know why we are using something called as a gradient descent. So what is this gradient descent? It simply says how to change your weights. The current most commonly used optimization technique is ADAM with a parameter of 0.06. Okay. Fine. So it changes the weights. Now, how is it changing the weight? I'm expecting this, but you're giving me this, so change it. Very, very simple when you have only one output. Okay. When I have just to assume there is no hidden node here. Okay. Assume there is nothing here. I give this, I get an output, I change the weight. Now there is a problem. I have it's not a single layered perceptron anymore. I have a 2-layered perceptron. That is, I know, okay, if this is not there, if this part is not there, okay, I know I give an input, I don't get an output. Based on how I want it, I change this weight and this bias. But now I give the input, I get an output. There is something else called the hidden layer here. I know what should be predicted in the output layer. So what I do, based on that, I change my weight. But how do you know what should be predicted in this layer? You understand? Only if I know what should be the output, I can change it accordingly. I don't even know what should be the output. I know what should be the output of the output layer. I do not know what should be the output of the hidden layer. If I do not know the output of the hidden layer, how am I going to change this? Okay, this is the problem at hand. I will, in another 15 minutes, I think we have just exactly 15 minutes. I will just run through this. Okay. So what we do is, so when you say you train an MLP, you want to learn the correct weight and bias. Okay. First you have a forward pass, then you have a backward pass. These are the two passes in this. Now, let's see some notations here. Okay. I will just try to tell you the one which is most important. Let's say an input of 0.2. Fine. So first you give it as an input to a node. And I'm having a activation here, which is a simple, how to say, it's called an affine transformation, wherein I just multiply the weights and the x. So 0.2 into 0.2, okay, plus the bias. Then I have to pass it through a nonlinear activation. I pass it through a nonlinear activation. Okay, I'm getting a 0.14. And then I give it as output. Output, I'm going to give it to another node. The output is 0.41. So it is 0.41 into minus 0.01 plus the bias. Okay. Pass it again through an activation function, get the output. Okay. This is called as the forward pass. Now, at the end of a forward pass, it has predicted an output. Now, the problem is, even though it predicted something, the output that I'm expecting is different. This is what we have been seeing so far. So the difference between 0.56 and 0.3. That is called as the error. Okay, that is called as the error. This error, actually speaking, I can just say it is 0.56 minus 0.3. Okay, that is acceptable. But to make things simpler during derivations, I am showing the error as a function rather than just taking the difference. It's what you call as delta, right? Okay. Instead of just taking the delta, I use a function to represent it so that the future derivations are easy. Okay. So for which here I have made use of a mean square error. Okay. So this error is 0.35. This I have to make it as 0. This is my objective. Now to make this as 0, I have to update my weights and my bias. Is this okay? Fine. This is the basic idea. Now with this basic idea, as we see, SGD updates for every sample. So what we do is, we are going to update the weights using a concept called as back propagation, or what we call as the backward pass. Okay. Now let's look at the backward pass. I think I'll use this slide. This might go a little faster because of the lack of time. Okay. So the gradient of the error with respect to the weight, we will take. Fine. Now, there is something called as a chain rule. Please have a look at it. Please note, I want to find this error with respect to this weight. This error with respect to this bias. But I do not have idea about the before part. Okay. So what I do is I make use of a chain rule. What does the chain rule say? If z is a function of y is a function of x, okay, and x is a function of t, then dz by dt is equal to, okay, dz by dt is equal to dz by dy into dy by dx into dx by dt. Okay. Now, how does it apply for us? The error is, let me call it as f of out O. Okay. But how do I get my out O? I applied, okay, please note, sigmoid activation function on the input. Am I right? How did I get out O? I applied sigmoid activation on the net input, which is given as net O. Then I gave it as, but how did I calculate the net input? Net input I calculated as, I took the output of the previous layer. Let me show you this. Okay. I took the output of the previous layer and then I calculated the net input. So I have three functions with me. That is exactly what I'm trying to show here. Okay. Let me stop all transitions here. Let me go through the slide again. This is the only slide that is required for back propagation. You understand this, you understand everything. You don't understand this, everything is gone. Okay. When I find the error, okay, the error is a function of the output that I get. How did I find the output? By applying the sigmoid activation on the net input. But how did I find the net input? I multiplied, okay, the weight and the output of the previous layer. Am I right? Very simply, if I say, to how do I get this? First, I will do this part, right? How do I do this? I will multiply the input and the weight and add the bias. Correct? That's what I have here. I will pass it through the sigmoid function. Correct? Then I will calculate the error. This is what I do. Now, I know netto, okay? I know auto, I know all this, but I do not know what should be the output of the hidden layer. So what I will do is, okay, I will use a chain rule wherein I try to find the error using just the information of the weight in there, for which I have to find, okay, differentiation of this with respect to this into differentiation of this with respect to this into differentiation of this with respect to this. Okay, this is not very easy. So what do? Find the error with respect to auto. Okay, what is the differentiation? Differentiate half into t minus out, you get it as minus of this. Okay, the reason you have used a half and the reason you have used a square there is obvious here. When you do a differentiation, everything cancels out. Then, what is the differentiation of out with respect to netto? That is very important. That is, you're trying to find the differentiation of the sigmoid activation function. Please note that. When you try to find the activation of the sigmoid function, there is a mechanism by which I can, that's a formula. See, these are all mathematical. When you differentiate a sigmoid, you can write it in terms of the original function itself. Okay. This is a sigmoid activation. I have differentiated it with respect to x. It is nothing but the original function into 1 minus f of x. Okay. I put that here. Then this information I have to see here. Now, what is the differentiation of this with respect to WHO? Normal differentiation. Wx plus b, if you differentiate with respect to x, it is just a w. Okay. So, what will this be? Everything which is independent of your w, you will lose. Okay. And you will just get it as out h. I have not done anything other than normal differentiation. So, when you want to, okay, I'll finish it in 3 minutes. When you want to find the differentiation, okay, you first find the differentiation with respect to this. Then you have to find the differentiation with respect to this. Then you have to find the differentiation with respect to this. Then you have to find the differentiation with respect to this. So if you see the number of multiplications that are involved in this. Now, if you look at it, okay, to get 1, you will multiply this, you will use the, what is that, chain rule, okay. When you're using the chain rule, just look at it. When I have just one hidden layer, okay, to find out WIH, I have to do 3 multiplications. But if I have, what are the 3 multiplications I have to do? The error with respect to this, then with respect to this, then with respect to this. But to find out with respect to this, I have to do another 3 multiplication. The only thing I'm trying to arrive at here is lot of multiplications you will do when you do back propagation. Okay, I have finished my time. So let me conclude back propagation by saying, 1, you make use of the chain rule. And the second, when you make use of the chain rule, there are a lot of multiplications which are involved in it. How does it affect us? If it affects us extremely. Every derivation that you do is a, okay, look at how many derivations you do, derivations you do, and you keep multiplying it. What happens when you have extremely big values, okay, and you keep multiplying? What happens when you have extremely small values and you keep multiplying? Can anyone tell me? what happens when you have extremely large values and you keep on multiplying? What is the effect? You get very, very large numbers. Okay? And that problem is called as the exploding gradient problem. What happens when you multiply small values? The multiplication becomes so small that finally it becomes almost zero. And you cannot find a gradient value at zero. This is called as the vanishing gradient problem. This exploding gradient problem is very easily solved, wherein all you have to do is, if the gradient goes before 5, always have it as 5. It's called clipping gradient. You just stop your gradient at a point. But this vanishing gradient is very, very difficult to solve, because during back propagation, when you have small values, it gets so much smaller when you keep propagating it to the before layers. There are many options here, okay, wherein it is not as simple as clipping a gradient, but rather you have to use a different architecture. So this is about ANN in general and back propagation in a small way. Okay. Now, any questions? Please let me know if you have any questions on deep learning, machine learning. I should be able to answer. Book, Sukesh sir, I could not find any book actually for this derivation. I have the entire derivation in my YouTube channel actually. It's a very, very, very long process. Okay, I will probably, I should be able to give you, it's a very long process, as I said. And the entire derivation is there in my, the whole problem is I keep forgetting my YouTube channel's link actually. That's my usual problem I face. I'll just give you my the link to my YouTube channel. This back propagation explained in detail with every single derivation I've done there. Every single line. Any other questions? And please note, it takes days to really understand this. So give yourself some break, okay? In the sense, please allow yourself to not understand. It is not very simple to just like go through it the first time and figure it out. I tried out all possible books, and then finally I thought, okay, unless I sit and learn on my own, this is not getting anywhere. And helpfully one day I got a whole day, I could get it done. I'll just share my link with you. As I said, I keep forgetting where to go and share it. Okay, any other questions? Thank you, ma'am. Thanks for your feedback. And what I wanted to teach today was actually back propagation, but what I ended up teaching was actually a totally different thing. I have no regrets about it, but because it's not possible to understand all this without knowing the basics for sure. Okay. I should be getting it.
Yes, ma'am. Thank you, ma'am. Thank you so much for the very lovely session, ma'am. Yes, the session was really nice. Ma'am, kindly share the PPT in our mail ID, ma'am. DLBC mail ID.
Okay, I've shared the YouTube link. Okay.
Yes, ma'am.
Okay. If bias input not one, what happens? Usually the initialization, usually, please note, it's just usually the initialization is 1. Okay. It is not going to give you a very wrong training if your bias input is not 1. It is just a very simple way of doing it. That's all. Any other questions? Thank you. Thanks, everyone.
Yes, ma'am. Thank you so much, ma'am. Participants, you can leave. The next session will be around 12 o'clock.
Thank you, ma'am.